Move to the tutorial from Tau. Professor Samir Sande will be presenting this. He has helped develop the Tau performance system, as many of you might be knowing. The Program Database Toolkit, PDT, the Extreme Scale Scientific Software Stack, E4S, and also the HPC Linux distro. Professor Sande's research interests include the tools and techniques for performance instrumentation, measurement, analysis, runtime systems, software stacks, HPC containers runtimes, and compiler optimizations. He serves as a research professor and the director of the Performance Research Lab at the University of Oregon, and as the president and director of ParaTools, which is also a sponsor of this conference. So let's give a very big welcome to Professor Samir Sande, and he will be presenting the tutorial on the Tau performance systems.
Hi, I'll be presenting the Tau performance system, and in this tutorial, we'll be doing hands-on. And the one URL you should go to right now, please pull out your laptops. This is a hands-on session. Every one of us is going to run programs using MVAPitch and Tau. We'll each have our own dedicated instance on AWS. And so the only URL you should need to see here is this one at the bottom. I'll keep it up while you open up your laptops. Yes, don't be shy. Just take out your laptops, go to e4s.io/tutorial. If you intend to do the hands-on, please reserve an instance. I've booted up about 50 instances. We can boot up more on the fly. So if you would like to do the hands-on, just go reserve an instance, and it will have instructions on how you can launch your instance in a web browser. So yes, there is software we will use, but you do not need to install anything on your laptop. You just need to go to a web browser, and you will be able to run all our tools, even our graphical user interfaces, all through the web browser. Okay, we are launching all these instances on AWS, so you'll be able to do this, and our participants who are online can also do this. So they can go to e4s.io/tutorial and sign up for an instance. 15 are there, 13. Excellent. So more of you should start. I've seen people do this even on an iPad, so you don't need to have any issues with connecting. Can someone just confirm that they are able to go here and grab an instance and actually launch it on the web browser? Yeah, all good? There are instructions over there. I'll give it another minute for you to just log into e4s.io/tutorial. There is a link to the slides there as well, if you wish to download them. And I would like to start by thanking the teams from the MVAPitch group and the Tau Performance team at the University of Oregon and the MVAPitch team at the Ohio State University for their contributions to this. A lot of this work requires many dedicated people, and this thanks the full team. The Tau Performance System, I've been working on this project for about 29 years. And it's a comprehensive profiling and tracing toolkit. It has support for instrumentation or adding hooks to your code, measurement like profiling, tracing, and analysis tools such as Paraprof, which will help you look at the performance of your application and figure out why it's doing what it's doing. Where is it spending its time? It's a widely ported performance profiling and tracing system, and it has support for data management, data mining tools. It is open source, BSD style licensed toolkit, and it uses performance and control variables to interface with MVAPitch software, and I'll describe this. We'll run some experiments. Its key feature is that it integrates very easily with application frameworks, and you can look at your performance of your application. And in fact, if you have a code, you can bring it right to this AWS instance, compile it with MVAPitch module loaded, and then run it right here. Each of you has a node allocated to them, and there are about eight cores that you can use. So it's a capable system. Now, Tau supports many different languages. We have hooks for automatic instrumentation for Fortran, C++, C, UPC, Java, Python, Chapel, even Spark. And we have support for many different runtimes. We support MPI, of course, MVAPitch, and we support OpenSHMEM, RMC, PGAS, DMAP, Eugenie. We have support for many different thread packages, pthread. We support OpenMP. We have the support for OpenMP tools interface and other hybrid thread models. For GPU runtimes, we support CUDA from NVIDIA, OpenCL, Level 0 from Intel. We support ROCm from AMD, OpenACC, and support for other external packages like PAPI, OTF2, ScoreP. And we have tools like Paraprof and PerfExplorer, and also a database, the TauDB database. And Paraprof has a 3D profile browser. So if you go to that e4s.io and you see the example, you can actually launch that browser and see. Now you're probably wondering, why do I need Tau? What can Tau do to help me? Well, it can help you understand where your application is spending its time and resources. At the function level, at the loop level, at the statement level, even at the GPU kernel level, where it can show you precisely how much time different parts of your code took. And instead of time, you can use hardware performance counters from packages like PAPI, Liquid. These will show you the precise number of floating point instructions, level 1, level 2 data cache misses, even off-core counters that are available on your system as they relate to your program code regions. one application, when you try to scale your applications to thousands of processors, one key question people have is how much time did my application spend waiting at a barrier in a collective operation? What was the useful part? What was the wasted part? Which collective operation? How much time did I waste in each rank? Time that could have been used more effectively if I had load balanced my application better. Tau can show you this with just profiling without requiring the full traces to be generated like some other tools. Tau can show you the time spent wasted at a barrier in collective operations. It can show you the memory usage of your code. When and where did your application allocate memory? What was the high water mark of memory usage of a process? And by that, I mean the total of stack, heap, data, text, BSS, the full amount of memory that your process used, and what was the high water mark during the execution. So you could make a rule of the back of the envelope calculation and say, well, each rank took about 2 GB. I have 32 ranks. I should use at least 64 GB for the application. So that number, the key number, where and when your application memory usage peaked, you will be able to see your I/O characteristics. Now, I/O is becoming more and more important as we scale our codes. You have many different file systems, right? You may have file systems from Spectrum Scale, GPFS, or Lustre, or RAM disk and DevSHM, or even files that are using some specialized hardware. You may want to know which files did my application access? Which files did I use on each rank? How much data did I transfer in megabytes? What was the peak value, min, max, standard deviation? What was the volume of data read, volume of data written? What was the peak read and write bandwidth associated with each file? You can get all that information. You can see the contribution of each phase of your application, even how your application scales, to look at charts like efficiency, runtime breakdown. You can ask questions like, how can I tune MPI for better performance? What performance and control variables does MVAPITch export to observe and control its performance? So there is a lot of information that the MPI runtime can provide to your application. And you can, in turn, tweak the performance of the runtime by moving those knobs. So you can do all that with Tau. And there are many ways to add hooks to your code, the instrumentation part, whether it's at the source level, at the library level, even at the executable level, where you can rewrite binaries, you can launch an uninstrumented binary, and then generate measurements for profiling, tracing, and then analyze them with our tools like Paraprof and other third-party tools like Vampire, JumpShot. To add hooks to your code to perform the measurements, you can use a source instrumentation approach, where you can use the Tau compiler scripts and a selective instrumentation file to then add hooks to your code, or use a compiler-based instrumentation. The compiler can add hooks at the function boundaries, entry and exit points. And we have a new release of Tau which supports an LLVM plugin. This plugin does intelligent instrumentation. For functions that are trivial, it will not touch them. The functions that have over 50 instructions, and you can change that number 50 by environment variables, it can add hooks to your code. So even C++ codes using Clang, LLVM compilers, or HipCC can take advantage of that plugin-based instrumentation at the routine level. But what is more interesting is that you can take an uninstrumented binary and simply launch it with a tool called Tau exec. So you say MPI run, Tau exec, and then the application. And of course, environment variables and parameters that you can set, like the number of ranks and so on. So the one key takeaway from this is to use tau, we will not change the application source code. We will not change the application build system. We will not change the application binary in any way. We will simply launch it with a tool called tau exec and generate performance data. Whether you're using CPUs or you're using GPUs, whether you're using CUDA or you're using OpenMP target offload directives with AMD GPUs or Intel GPUs, or you're using any other type of CPU GPU combination, you simply launch it with a tool called tau exec. Does that sound okay? Okay. And we will show you that in this example. In fact, when you launch that e4s.io/tutorial, there is a little blurb on if you wanted to get started. For those who are anxious, you can go to that directory, you can launch that command, and you will actually see that you are compiling the code and using an uninstrumented binary and simply generating all the performance data. Okay. So how do we use this AWS instance? If you are using your own code, you simply say module load mvapage2. It will load the mvapage software in your path. So MPI-CC comes from this. And this version supports the Elastic Fabric adapter for EFA on AWS. You can build your code and you run it like this. When you use tau, you will simply say tau exec with a tag of mvapage2, and then you say event-based sampling, or periodically interrupt my program, see the program counter associated with the source line number, and then generate a profile file. So EBS is event-based sampling, and I'll speak about it tomorrow in my talk, but that's all there is to it. You just say tau exec with these parameters and the application binary, and then you launch it, the performance data with paraprof, view it through the GUI, or we have pprof, you can say -A to see the source line number, and see the text output from pprof. That's it. Now, this AWS instance has the GUI tools built in. You should be able to see it through the web browser and check it out. So here is an example of using tau with different GPUs. On this AWS instance, we don't have AMD GPUs or these other GPUs, but if you had configured tau on your own system, if you had an AMD GPU system like the Frontier system at Oak Ridge, you could say tau exec-ROCm. If you had an Intel GPU system, you could say tau exec-L0 or level 0. For CUDA, you can say -kubT or unified memory with -UM. OpenCL, OpenACC, plain MPI is just tau exec. With event-based sampling, it's tau exec with EBS. There's memory, IO, even OpenMP tools interface, OMPT. And when you configure tau, this is an important slide. When you configure tau, you build it with many different options. You can say, I want to build it with mvapage, or one with mvapage with pthread with MPI tools interface, the bridge between the tool and the runtime. And then you can have multiple of these configuration make files where they encode the path to the MPI, the path to the compilers, and you can choose one of these tags in the make files by using the -t. So when I say mvapage2, MPI-t, I'm choosing this configuration with the MPI tools interface, with pthread, MPI, and program database toolkit, which is a source-to-source analysis toolkit. And I say tau exec-t, and then pick one of these tags and the configuration that I have used. So here's an example. If I configure tau with PAPI and without PAPI, I get this make file and this libtau.so, which is in this shared library with the tags. And now if I say tau exec-t with the PAPI MPI PDT, it picks this configuration. If I choose without PAPI, it picks this one. So you get the idea. You just use the tags, and then if you want to just see a dry run, you do it with a -s. So without MPI, you use the -t serial. This is how you install Tau on your, yes. No, it is event-based sampling. What it means is it interrupts the program periodically. It collects samples. And based on the number of samples collected, it can show you what the rest of your code is doing without program instrumentation, which will show you the line number, the source information. And we'll use this in our hands-on. This is how you install Tau on your laptops for Windows, Macs, or Linux. And we will use this e4s.io/tutorial, connect to this web browser, put the login and tutorial. Raise your hand if you have had trouble connecting to this instance. You are not able to connect? Pick another instance. If not, SSH to that tut using a web regular terminal session. If you picked 46, then say SSH tutorial at tut 046.supercontainers.org, and then you should be able to use that. But for anybody else, are you able to connect to the web browser? Yes. And so we will just look at some examples. Here is the first one. This is a molecular dynamics code called CoMD. It comes from the Exascale Computing Project's COPA Code Design Center for Particle Acceleration. It's a MD code. We'll say, go to the bin directory. We'll run this script, which actually does a make clean. It does a module load mvapitch to, it then does a build, and then it runs your program with Tau, and then we'll see in paraprof. You can also try this demo.ppk file, and then here are some other examples of an all-reduce collective algorithm. We'll choose different collective algorithms. You can look at the README file there, and then there is an all-to-all directory. There's a 3D stencil directory where we'll do advanced auto-tuning with this. So we are at 9:46. We have till 10:30. A lot of time for hands-on. This is what we are here for today. So we'll do these sessions, and of course you can download Tau from these locations. e4s.io is the extreme scale scientific software stack, and much of our work goes on at the Performance Research Lab at the University of Oregon in Eugene. Please consider coming to Eugene to visit us. It's very nice in the spring and fall and summer. And I would like to thank our sponsors at the US Department of Energy, at CEA France, at NSF, Department of Defense, NASA, and our sponsors, including AMD, AWS, Broadcom, Google, IBM, Intel, NVIDIA, OCI, and our partners at other universities like the Ohio State University, Paratools Inc., the University of Tennessee, Knoxville, TU Dresden, and ULA Supercomputing Center. And I would like to thank the Exascale Computing Project for sponsoring this work. I have some reference slides here. I have uploaded my slides, and you can go to the e4s.io/tutorial and download the slides from there. And this is how you install Tau. These are some compile time options, references for runtime environment variables that you can set. And we'll set some of these so you can get a sense for using Tau. And let me with this go and do our hands-on. Okay, so with this, let me just go to display. Scaled. Make it bigger. Okay. So at this stage, you should have a terminal window. I'll just go and pick an instance. So here I'm picking, say, Tute 004. So I'll go here and go to tute004.supercontainers.org and connect to this instance. Now here, it asks me for my username and password. Okay, so I will go and put in tutorial and then the password which is there on that site and click login. When you exit, please don't use the exit button to log out. Just here, let me choose 14. Are you able to log in properly? It had a problem? Okay. So glad to hear that. So I'm just going to 14. So if you do touch an instance, please mark it out so that nobody else tries that. Okay.
You selected 11, not 14.
Oh, I selected 11?
Yes.
Sorry. Then I should, thank you, Jody. I selected 11. Okay, so we are set. You see a remote desktop screen at this point. You should be able to click on this GNOME desktop terminal and then launch this. I hope this works for everyone. Any problems? Okay, so let me just go and make it a little bigger so I can zoom in so you can see the screen. Okay, now the first example that we will see is an SRC demo CoMD example. The O is lowercase, and then I'm just going to go to the bin directory. There is a rmv2.sh file here. Now in this example, what I'm doing is I'm loading the mvapich2 module. Then I'm going to the src mpi directory. I'm doing a make clean, then make, and then coming back to this bin directory. I'll set some environment variables. I'll say turn on call path profiling. Turn on call path profiling to a depth of 100. Track the performance variables from the MPI tools interface that mvapich provides. And then I will run this code, which I normally run without the tau exec command, but I'll run it on 4 MPI ranks. With the tau exec, I'll choose the tags as MPIT, mvapich2, turn on event-based sampling, and then run this CoMD application. What I'm trying to do here is, I want to find out where is this application spending its time. Okay, how much time is spent in different MPI operations? What is the value of performance variables that mvapich exports? So can you all go to this src demo CoMD bin directory and then just run this rmv2 script.sh. That's all you have to do. Type in /rmv2.sh. Is this running for everyone? Just a show of hands. Yes, good. So it's compiling the code. It is running it with mvapich2. And you will see that we will run it with tau exec with an uninstrumented binary. So I didn't need to change the source code. I didn't need to change the build system. I didn't need to change the binary. I just launch it with tau exec, and there it is. It runs, and it will generate some profile files. These profile files can then be loaded in the paraprof tool. Everyone with me so far? Okay. So here I'll say paraprof, and then I will launch this like this. Now, the reason we have this remote desktop is because then we can use the graphical tools all from within the web browser through this DCV environment that AWS supports. And I see those 4 MPI ranks which show up as node 0, 1, 2, 3. Let me go over here and right click in this region, not on the colors which represent the functions, but I'll go here and right click here. When I right click, I see many different windows. For those who are using Macs, please use two fingers to right click. And then let's choose the thread statistics table. So find out what this particular rank is doing. My goal is to find out which functions, which lines of the code are spending how much time, right? I just ran this on 4 MPI ranks. I launched it with Tau exec. I go to show thread statistics table. Please try that with me. And you should see that it took about 13 seconds to run this code. If I open this and I see all the MPI timings and all, it tells me that MPI send receive took 1.5 seconds here. The rest of the code over here, you can see. If I can click here and click here again, it tells me that outside of MPI calls, and we'll go into MPI calls later, outside of MPI calls, the application spent about 7.9 seconds. You can see the Tau preload main exclusive time, that is excluding what is there in the other functions. It spent 7.9 seconds. Now this is with entry-exit probe-based instrumentation. With sampling, we are periodically interrupting the program. It is imprecise. It gives you an estimate of how much time is being spent in the code. Sampling cannot explain the full 7.9 seconds in the program. It can only explain 7.772 seconds. Do you see the context window here, which says over here, this is 7.7, this is 7.9. This is what is outside the MPI calls, roughly 7.9 seconds. With sampling, I can explain 7.7 seconds. It's close enough, right? 7.77 instead of 7.9. Let's open up the preload main and figure out where is the code spending its time. So I'll expand this key again, and I'll come to this. Here, it shows me that there are all these functions. I collected 259 samples. I collected 259 samples, and it explains 7.7 seconds. And then there are many functions. There are functions like sort atoms in cell, get box from coordinates, put atom in box, molecular dynamics functions. They don't account for anything. There is only one, which is LJ force. Do you see the yellow little function where my cursor is? That LJ force function is taking up 244 samples, and it takes up 7.3 out of the 7.7 seconds. Okay, that's the one, that's the main function that it's saying, look at that. The other functions don't matter. So I can expand this, and it will show me the line numbers. It says in line 198 and 199, I spent 1.29 seconds with 43 samples. I spent 1.1 seconds with 37 samples. Look right there to find out the code region which is taking time. So I can right click here and say show source code. And here is the source code of 198 and then 199. Now I see that it's in a for loop. But there's not just one. There's 1, 2, 3, 4, 5 levels of for loops. And that's the line of code that it's saying right there in that LJ force function, that's where your application is spending time. So it can drill down immediately. So if you had to run your application and find out where it's spending time in a relatively short period of time, you could just launch it with tau exec, jump to paraprof, go to the show thread statistics table, and you'll be able to explain line by line what's happening in your code. Can everyone try this and say show source line number and get to this view? Here, what I did is I ran paraprof in this directory, the bin directory. I right-clicked here. I said show thread statistics table. When I did this, I got that. I opened it up. I can click here and sort it by different ways. And here, I click this summary for LJ force. And I click here. I look at the line numbers, look at the inclusive time, go to this line, and then simply say show source line number, and there it is. Is there anyone in this audience who's an expert in molecular dynamics? Does anyone know MD codes? TSMC code. Can you look at this source code over here? These are 5 levels of loops in this LJ force routine, Leonard Johnson force calculation routine. Do you expect that to be taking time? It looks like the distance evaluation between these atoms. Okay, okay. So that's the exact line of code in your code where it's saying this is where you should focus your attention. And how easy was it to get to that? You know, you just go down, sort it, say this line number, show me the source code, and you have the application function, right? We have other
Dr. Shende, we have a question in the chat.
Yes,
are you okay
please.
if I take that?
Can you read it out, please?
So I've unmuted him, so Narul, you should be able to speak.
Yes, go ahead.
You can unmute yourself.
Go
No,
ahead.
I'm sorry. I incidentally pushed my right hand. So no question.
Oh,
So sorry for interrupting.
Okay, no
Thanks.
questions. Is this working for everyone? Just a raise of hands. Are you able to go here, launch this? Okay, and look at the source code in a paraprof browser window, see what's happening. Remote people, are you also able to log into these instances, launch this tool? If you are looking for steps, I'll repeat. I went to this directory called ~src demo comd bin, and then I ran this rmv2.sh script. This script did a module load mvaph2. Very important to get the MPI compilers in your path. Did a make clean, make, go here, and simply run this code on 4 MPI ranks. Is this okay? And once you run this, you can say paraprof or pprof and simply launch the browser window. When you launch the browser window, it will bring up the manager window and the performance data pane. And then I go right click here, node 0, and say show thread statistics table. Since it's a tutorial day, we are all going to do hands-on. That's a given. And we're going to go log into this and try this and open up the GUI over here. Now I'm going to look at what's happening in the MPI send receive. You see, here is the MPI send receive, and I can even go inside that. Yes, you heard me right. I can go peek inside the MPI runtime by looking at the summary and see exactly what's happening. Here is a line of code which is taking, so I can say, show me the function bar chart, and it will show me the exact line numbers for what's happening inside the MPI. Now, send receive is calling a function called MPIDI ch3i SMP read progress. And it happens to be in a file called ch3 SMP progress.c at line number 1097, and it's taking this time across all the ranks. You can see inside libraries whose source code you do not have. Let me repeat that. You can see inside libraries whose source code you do not have. It could be libraries from vendors like Intel, AMD, NVIDIA. It could be libraries from other vendors who are seated here. Sometimes they will remove the symbol information, in which case you may see unresolved, but you will still see the name of the library. If they have forgotten to remove or strip the symbols, using the strip command, then you can see exactly which line number in which file, even if you don't have the source code. Okay, and sometimes you can just Google for the name of that file and it will show up with close to what it is showing. So you can see what the code is doing internally with sampling, with all of that information. Then you can also, and I do not expect you to reverse engineer anything. This is just for your information, okay? So just look at the names of routines and ponder. Look at the names and say, oh, this is doing progress. Here it's doing a write progress. Here it's doing a mem move AVX unaligned. You see the line number there is 0. And sometimes you'll see unresolved. So you will be able to look inside libraries. Here is MPI all reduce, collective operations. There's a collective sync. Collective sync is the time spent in MPI waiting at a barrier. Waiting at a barrier. Now, do you see that this MPI all reduce called this collective sync? And it was called 5 times, and it spent 0.15 seconds. That's very nice, right? The program spent 13 seconds. Only 0.15 second was wasted in a barrier. The efficiency of MVAP-H2, it spent only 0.15 seconds in a barrier, and then you can see what it was doing when that collective sync was taking place. So you can get detailed information about this. Here I will close this window and I'll go to the right click and say, show me the user event, context event window. Show context event window here to look at the performance variables. You see there is a bridge, the MPI tools interface, and I can see information exported by the runtime. All of these performance variables that MVAP-H supports, and I've worked with a half a dozen or more MPI implementations. I think MVAP-H2 has the biggest collection of performance variables that they export, and also a very rich collection of control variables, the knobs you can use to tweak the performance of your code. And you can see all of these collective operations and the counts that the performance variables show up over here. If you want to see which control variables I have access to, you can simply go to the manager window and expand this with the metadata. It tells you more about where the code is running, but also all of these control variables and the complete text of what that control variable is. Here, for example, is the MVAP-H MPI TC var with the all gather long message size and eager thresholds for changing the operation of a collective operation from eager to rendezvous, at what size that switchover takes place. You can set all of those things using tau, and it will modify the runtime. If you want to see this example, so first of all, is this okay? Are you able to access this, run this code properly? Look at the CoMD example. Let's look at a 3D stencil now. Here we will see a interaction between the application and tau, where we set control variables, where we dynamically change the behavior of the default operations that are happening. So I'll go to the 3D stencil application as we have shown in the slides, and I'll go to 3D stencil. I'm saying PWD. And we've made it easy. We're going to just run this run.sh script. And it's running it 3 different times. I do an ls over here. I don't see any performance data here. I'm going to say run.sh. Again, everyone go to the 3D stencil directory in src demo 3D stencil. cd to src demo 3D stencil and do a run.sh. Take a minute while you do this. Are you able to run this code? Any questions online? I hope our online participants are also able to log into these AWS instances, just as if we were here, and just run this code, 3D stencil, and run it. There are 3 cases. One is the default case, where we'll just look at the performance of the application in the default mode. Then we'll change the eager thresholds. Then we'll do an adaptive change of the MPIT control variables. So I'll run it. It's compiling the code with MVAPitch2, and it's going to run it. Here it's running it, and then it changes the eager threshold. You can see the MPIR, and then it's going to run this again with the adaptive control with a auto-tuning plugin. I repeat that, auto-tuning plugin. And I'm going to launch Paraprof, not just one with one experiment, with multiple experiments. You see, with her profile files, I can always pack them and say paraprof --pack foo.ppk. It will pack all the files in a file called foo.ppk. I can say, look at the ppk files. Now, you will actually get a lot more out of this if you are running it on an HPC system where you have thousands of nodes. But just for a simple example, I take this and run it, this 3D stencil, on our 8th course of AWS. Paraprof star.ppk, so that you can load up all 3 of them at the same time. Is this okay? Paraprof star.ppk, load up all 3 files. So you can see what it did. This is the default, node 0. This is the auto-tuning, and this is the eager. Now I can right click on any node, and I can add it to a comparison window. So I right click here on node 0, and I say add thread to comparison window. I want to compare all 3 of them I want to compare node 0 of this default with node 0 of, say, Eager and node 0 of auto tuning. So can you all try this? You have done run.sh in the 3D stencil, and then you launch paraprof star.ppk. You right click on a node and say add thread to comparison window. So I go here. Let me change this exclusive time to inclusive time. So I can go to options like this, and I can say select the metric as inclusive. So I see the total time from the start to finish. Okay, I can say inclusive time is here. And then I can look at other examples. So typically what happens is you can compare the performance of multiple of these instances on an HPC center. Here, everything is running on the same node. So the opportunities for this kind of a experiment are limited because it's just on the same node. They're just 8 ranks. But on other HPC sites, you'll see a much bigger difference in terms of being able to optimize the code at runtime. Okay, here we are looking at just 6 seconds of execution. So this is just to show you what is possible on a bigger system. It's not to actually look at the performance data generated, but just so that you can compare with one with the other and then see the performance. So here, for example, with Eager, it shaved off 5% even on this instance. And if I look at the auto tuning version, let's look at node 0 at 3%, and it shaved off 6%. So there was a slight difference in the performance of the code without changing the application binary. So even on a small AWS instance, I could get 6% reduction in the runtime by changing what the MPI runtime is doing. Okay, without changing the MPI libraries, without changing the application binary, by just tweaking the performance at runtime by changing variables and saying, use this, don't use that. And I can get some benefit. Even here, it's like 6% benefit with auto tuning. So just imagine having a script, you just run that script, it loads plugins from the Tau performance system. During execution, it monitors the MPI, it talks to MPI, it changes what the MPI is doing, and then it improves the performance. Auto tuning with Tau, and you can see a small benefit over here as well. Do you also see benefit like this? Are you able to run the same code and see that maybe one is doing a little better than the other? Any numbers, so to say, what percentages are you seeing? Again, what I did is I went to this directory, 3D stencil, I did a /run.sh, and then I did a paraprof like this. I hope this is not too complicated, right? It's okay, right? You just go to a directory, say run.sh, launch paraprof, and see the performance data like that. And once you do that, you'll have the 3 different windows, and you'll be able to see how these modifications work. Any questions so far? Is paraprof working okay? Yes? Yeah, just hold on.
So yeah, I have a question about how we built the application when we wanted to enable the tau profiling. So I saw that you enabled a couple of variables, the mvaph2 and the MPIT. So what did we gain by enabling these, as opposed to just enabling the event-based sampling?
So I said -t as in a tag for tau exec. There are 10 configurations of tau. I'm saying I want to see the MPI tools interface pvars. So I'm choosing the configuration that supports MPIT. And so the -t was just to specify that use this configuration of tau. It was not modifying the application in any way. That is very important. You did not need to build the application in a separate way. You just build it with make, just with mvaph2 loaded as a module. And then you're just saying tau exec, use this configuration, and then also enable event-based sampling. So with the -EBS, you can look at the application and then see what's happening inside that. So then I'm able to see variables like these context event window and all of these performance variables from mvaph that I can see in the context event window. I can also see details of the thread statistics table and other things that are happening in the application code. And in this case, I'm just seeing the application binary and the total time taken by going to options, select metric, inclusive, and then I can see that this was taking 5.9 seconds. And if I go to the other one and just go to this eager, I can see add thread is over here. So like this, you can monitor the difference in performance of the application.
Oh, am I audible?
Yes, yes,
Okay.
go ahead.
So a follow-up question on the event-based sampling. Is there a recommendation for, the number of samples to be taken from the application, or like the default value will always suffice?
The default value is good enough, but you can change the period, the frequency of sampling by setting another environment variable in tau. We have a whole list of them in the table that I showed. And a rule of the thumb is that if you collect more samples, then it is more accurate, right? If you try to collect samples and if the sampling period is 30 milliseconds and your code is running for 300 milliseconds, you only collect 10 samples, that's not a whole lot. If you are running for 1 hour, then you can be sure that it will pinpoint exactly what's going on and help you get to that point.
Thank you. Thank you very much.
Am I audible?
Yes.
So the question I have here is, so since I understand that you can have like multiple levels of hyperparameters while profiling with tau, but what is the overall overhead in terms of time running an application with tau? And not just time, but memory and other performance implications of executing tau?
That's an excellent question. That's an excellent question. Maybe let's just look at some code here. Demo, let's go to say NAS parallel benchmark, module load mvaph2, make clean, make, will this work? And unrecognized config make.def. This is on the fly, as you can see. Allow. Okay, let me remove this make suite. Let me build an application full with the optimization flag turned on. Let me turn on the full optimization O3 level and run this code on our instance. Okay, I have this LU benchmark. LU I have chosen because it has a lot of communication. So the overhead will be higher because there are so many more messages going through. if I say tau, let me just run this first with lu.b.4. Okay. See, lu.b.4 is running. It'll take some time. It's exchanging a lot of messages. It's using mValpage. And at the end of this, I will run it with tau exec with event-based sampling, the defaults. And let's just compare the performance. I think this code also prints out as a default, how much time it takes. How many of you have used the NAS parallel benchmark before? A whole lot of you, right? So it's a standard that we use for publishing all our papers, right? We run it through NPB and see the performance. And it's taking time. So this is a good example of using sampling with full O3 optimization. All I'll do is I'll run it with tau exec with EBS. And let's see how long it takes. There. How much time did it take? I think it went up. Here. Can someone remember this? 71.52 seconds. Okay, a little over a minute. Now, I'll say MPI run -np4 tau exec -t mValpage2 with event-based sampling lu.b.4. Okay, let me just also see ls. See, there is no profile data before. And see, there's only lu.a.4, lu.b.4, and no profile data before. And now it's running, and it was what, 71.52. Okay, so let's see how much more overhead we add to this MPI execution. What is an acceptable level? That's another question to ask. 71.52, what would you say is okay for the run with full event-based sampling? Would you say 75? 80? What is acceptable? 5 to 10%, right? 10% overhead would be 7 more seconds added to this code. And it's taking those samples every 30 milliseconds. And let's see, 71.54 seconds turns into, it's always fun to do something on the edge where you don't know what will happen. It could be like 100 seconds. And there, it finished. But I don't know how many seconds. I'll just scroll up slowly with much trepidation. Oh, it went up. 69.41 seconds. This is fun. So it's not much. I did not expect that. So what's the takeaway? To optimize your code, you could just run it with tau exec, right? And of course, you will get the profile files, but that's just an added benefit. There is the time spent, and I can look at it and see the statistics table, and it's showing me the time spent in MPI receive, it's showing me the time spent everywhere else. And with that, we will we'll close this. If you want to try this, there are 3D profile browsers in Paraprof. I did not cover that. There's a fun example here, and you can just say Paraprof demo.ppk, and with this we will take a break, and you can try this demo.ppk, go to Windows 3D visualization and look at the bar plot here, rotate it with your first mouse button, all the MPI ranks, all the functions and the time spent in different functions. You can zoom in, zoom out. You can look at this and try this example. You can also use plus minus buttons to zoom in, zoom out, and 2-second mouse button to translate. So with this, thank you very much. Please attend the other talk tomorrow.
Let's give a big hand. So Professor Sunday has a magic. You can use Tau and run your programs faster while turning on his features. He will be here throughout today and tomorrow. If you have any questions, please feel free to interact with him, and he will be very happy to answer. So we'll go through a coffee break. I also want to indicate there are a lot of posters from the students here, as well as we have many of you have come through an NSF student travel grant. I'll talk about that tomorrow, but their posters are also here. We'll have an official poster session tomorrow afternoon, but during the break and lunch, please feel free to interact. And then if those people who have posters, if you can